In this video, we're going to solve a practice question on fixed cost formulation. Question number 4 from chapter 12. So in this question, we have a manufacturing company that are producing connecting rods for 4- and 6-cylinder automobile engines using the same production line. So, and then we have the setup cost for 4-cylinder connecting rods and the setup cost for the 6-cylinder rods. We also have the per unit cost or variable cost per unit of 4-cylinder and 6-cylinder rods. And well, I mean, there are some details in that, for the working hours during the week. But then in each week, the maximum production or the production capacity, weekly production capacity for 6-cylinder and 4-cylinder. Again, we do have these numbers: 6,000 for 6 cylinders, 8,000 for 4-cylinder connecting rods. The question actually defines the decision variables for us. So we have the X4 and X6, the number or the amount of rods to be produced in 1 week, next week. And then since we have fixed cost, and for fixed cost, we need to know whether or not we are producing, whether or not X4 and X6 are positive. We have to define two binary variables, one for each type of product, right? So we call this S4 and S6, one for 4-cylinder, one for 6-cylinder rods, all right? So we have the definition of the decision variables, and then the question asks us to write down the constraints and the objective function. So for the first one, part A, using the decision variables X4 and S4, write a constraint that sets the next week's maximum production of the 4-cylinder connecting rods to be either 0 or 8,000. So this is a connecting type of constraint where we connect the continuous variable with the binary variable. And the way we connect that is by this continuous variable less than or equal to the binary variable times a large number. Just put large number. And large number in this case is the maximum capacity, which is 8,000. So for part A, the continuous variable is X4, which is going to be less than or equal to the 8,000 times, or large number in this case, times the binary variable, which is S4. So just look what happens. If S4, which is the decision about the production at all, if S4 is 0, then X4 is going to be less than or equal to 0, which is going to be equal to 0 at the end of the day. So if we don't produce anything, if we decide not to produce, then the amount of production has to be forced to be 0. But then if S4 is 1, X4 will be less than or equal to 8,000. So it can be any number between 0 and 8,000. So that's what we are trying to do. We're trying to connect these two variables by holding the logic that has to be true between these two. So that's for part A. For part B, same thing, except that we're doing it for 6-cylinder and the maximum capacity is 6,000. So X6 less than or equal to 6,000. S6. In part C, write a constraint that requires that production be set up for exactly one of the two rods. So we want to enforce a constraint that only allows us to uh, produce only one of these two products. So among 4-cylinder and 6-cylinder, S4 plus S6, so 1 out of 2. It's K out of N type of constraints. It's going to be exactly equal to 1. So sum of these two, the binary variables corresponding to 4-cylinder and 6-cylinder should be 1. And for the last part, write the cost function to be minimized. The cost function that we want to minimize is going to be the total cost. So objective function is going to be minimization of cost, and cost has two components, a fixed cost and a variable cost. So we have to spend 2,000 if we produce 4-cylinder. So S4 plus, and then we have to spend 3,500 if S6 is 1 plus. So this is the total fixed cost that we have to pay. And then we have a variable cost. For each 4-cylinder rod, we have to pay $15. 15 times X4. So X is the number of units, number of rods that we're producing, multiplied by 15 is going to give us the variable cost plus 18 times X6, the amount of production of 6-cylinder connecting rods. So that is going to give us the objective function.